And we just started the stream with oh. Hello and welcome back to the oh class. It's a Precalculus 1 drag for today. We will be talking about applied problems again. And we're going to work on a few more of those either decay or growth problems. So let's take a look at the text here. So last time we did not talk about carbon dating. So carbon dating is a technique where you extract carbon from whatever you dug up and you examine how much carbon is left, and then you run through this mathematical procedure which tells you how old the stuff that you dug up is. It is good for anthropology. You take a look at old dishware or remnants of a fire or houses that use wood in it. You can't carbon date the stone, it's not organic. So there's a lot of organic materials, also very good for paintings, old paintings. All of the color was made out of flowers, so organic. So carbon dating is something that it's possible for us to use to figure these things out. So now let's see. Exercise 19 through 14, complete the table around the problem. Okay, so we're just going to put one of these problems, and it says oh wait, this is the, sorry, 9 through 14 is not on carbon dating, it's on population. Let's go with where's the only one? Wow. Trying to find carbon dating problems. There it is. Skeletons were found at a construction site in San Francisco in 1989. The skeleton contained 88% of the expected amount of carbon C14 in a living person. How old are the skeletons? So, the skeleton was found in 1989 and it contained 88% of C14, which is the carbon isotope. How old is the person? Well, yeah. So let's first find out the half-life for carbon C14, which is actually given to us. You can also look at the you can look online, but the carbon C14 has a half-life of 5,715 years. And now we see that it's 88% left. So we know that our model is that the mass of the carbon is the initial mass of the carbon times e to the negative kt, where we could just say kt and then the negative will pop out. Just make sure that stream is going. Yep. Yeah. And what I'm going to do now is plug in half-life, so half of the original mass will be gone. And then we have for time lambda, which is 5715. The mass will cancel. We will introduce ln to both sides and have ln of 1/2 equal to ln and e cancel 5715 times k. So from here, k is equal to ln 0.5, that's a half, divided by 5715, and we use our abacus to calculate this. Now you will need the calculator for your next exam because of these calculations, and you always make sure you keep 4 decimals. So I have ln 0.5 close parenthesis divided by 5715, which gives me negative 0.0, 1, 2, 3 zeros, 12, 13. So this is the K. So now I have the model, which is this. T. And now they want to know how old. So how old implies that T is equal to question mark when 88% of the original mass is left. So 0.88 of capital M is left. The M's drop. Again, you ln both sides because you want to get rid of that E. And you get that ln of 0.88 is equal to negative 0.0001213 T. From where T is equal to ln 0.88 divided by negative 0.0001213. So ln of 0.88 divided by 0.31213, 1054 when you round. You don't, please don't use 4 decimals for a year. I just whole number rounded to whatever is. So time equals, maybe over here, time equals 1054 when you round. So that's how old the skeleton is. No need to call the police. That's called carbon dating. How about we use this, make a turkey now? Yeah. Newton's law of cooling. It falls in this category. Yeah. This is how I make my turkey, because I don't want to sit there by the oven, check, put everything in, take it out in 30 minutes, measure the temperature, do the calculation, set the timer down to a second, and then you don't have to worry about it. Let's see how that works. Welcome.
Sorry.
So Newton's law of cooling, that's on your page 472. Now it's not just cooling, it's also heating, because you are heating So the temperature of the turkey eventually is going to be C plus T0 minus C e to the kt. So the T0 is the initial temperature. C is the room temperature. Capital T is final temperature. And obviously K is the constant and T is time in hopefully minutes or hours, not in years. Put the turkey in the oven, come back in 7 years. It's ready. So let's see. First, we want to find out some properties, properties of the oven, because not each oven is the same. I have electric oven, gas oven, wood burning oven, right? All different types of ovens. And the property of the oven included with the dish in which you're cooking and all of that stuff is within the K. And for different ovens and different dishware, you might use K is the one that gets adjusted. So let's take a look at what we need. And this was on my Calculus 1 project 2 years ago, I believe. And the students did take the pictures of baking. You can do the chicken, you can do the turkey, doesn't matter. So students got together and actually did bake and measured and took the pictures of everything, and it was on a project. It was a cool experience. So what are we doing here? Well, the first thing that we need to figure out is what are the specs of the situation, meaning what's the temperature of the turkey before it goes into the oven. So let's pick a value for turkey before oven. So what is the temperature of the turkey before oven? No, that's a freezer. Yeah, it will be room temperature if it sits on a counter. You don't make a turkey. Huh? In a freezer, you preserve it. Yes, you let it thaw. So what would be the temperature of it? No, the turkey. Room temperature. So 70 degrees. All right, 70 degrees. Turkey before oven. What's the oven temperature? 400. 400 Celsius? You're not melting metal. All right. So let's see. I also need to estimate now, because we can't do the experiment, temperature of the turkey after, let's say, T equals 1/2 hour. So you let it sit inside the oven for ½ hour, and then you take the probe and you check the temperature. Yes. 400 degrees.
Are we allowing setting time to cook it as well?
I'm sorry?
Are we allowing setting times to cook it as well? So like you take it out while it's still a little raw, that way it finishes cooking while it's outside the oven.
No. It's going to be perfect temperature when you take it out.
Then it'll overcook. How long do you keep it?
It's a math problem.
How long is it?
So we have half hour. So what would be the temperature? Remember, it was 70 degrees going into the oven. How much would it be after 30 minutes? That's what we're trying to find out. To find K. We are doing the good old-fashioned method. None of this stuff that they have right now where they tell you on a package what you do. Lame. Anyone? No takers? All right. 79 degrees. Whatever. And then I need one more piece of information, and that is, what is your target temperature for the turkey? What's the target temperature?
Like when you're eating it or when it comes out of the oven?
When it comes out of the oven. 165. We'll talk after class. No, it's going to get cool. There's another math problem you can actually figure out using the same formula. How long should it sit before it's perfect temperature to eat? All right, let's go. So now, what do we have? We are going to take the turkey and put it in the oven, and we are supposed to see, right, how much is K. Now, what do I have? I have the temperature, initial temperature of the turkey, T0. So step 1, initial temperature T0 of the turkey is 70 degrees. Then I have the room temperature in which turkey is going to reside for half hour, which is 400, okay. And we have the target temperature is 79 degrees, was the temperature, that's when we check. And the time is 1/2 hours. So you see that we have everything that is needed to compute that K. Once you compute the K, you can plug in the rest to find out how longer you will need. So now let's go. Calculate this real quick. The temperature is equal to, we have the room temperature plus T0 minus C e to the KT. All we need to do is to plug all of these values in. So 79 is equal to 400 plus, in parentheses, we have 79 minus 400 e to the 1/2 K, right? T is a half. Oh, yeah, 70, thank you. Temperature of the, yes, initial temperature of 30. So now we have negative 321, when you move 400 to the other side, is equal to negative 330 e to the 1/2 K. So now we are going to divide negative 3. Remember, in order to apply ln to both sides, you have to have e alone. So 321 divided by 330 is 0.9727 equals to, leave space, e to the 1/2 K, so that we can put in ln on both sides. So they cancel on the right. And what I have is ln of 0.9727, and then I will multiply that by 2 to get K. So K for this particular oven is negative 0.05536. And I have K. Now this K is the one that actually describes the dish and the oven and all of these features that you have. So now we have that the temperature is equal to C plus T0 minus C e to the negative 0.05536 T. If you're a little bit confused, just understand that this is Newton's law of cooling, which means when it's negative K, it's heating, right? Because if it's called Newton's law of cooling, then positive K's will be cooling, and then negative K's will be heating. Same formula is used to cool down stuff, except your K's would work out to be positive. So now I have a mathematical model, and I want now to compute how long do I need to wait. So the target temperature is 165. The room temperature for Turkey is still 400 degrees. Plus now initial temperature is 79 because remember, we took the turkey out, did the measurement, and the turkey is going back in. We're starting a new problem, starting calculations from scratch, but the turkey is already at a 79 degrees. So 79 minus 400 times e to the negative 0.05536 T. Do the subtraction, negative 235 is equal to negative 321 e to the negative 0.05536 T. Again, the same calculation, divide, so we have 235 divided by 321, 0.7321 is equal to E, leave space, for ln. We ln both sides, and we get ln of 0.732, no, yeah, 321 is equal to negative 0.05536 T. And then you divide. So ln of 0.7321, close parenthesis, divided by I'm getting 5 hours and 64 minutes. No, 5 hours, 0.64, so more than 5.5 hours for this particular. Now, these were all approximated. Guys, I tried this. It works like a charm. I actually did this on the turkey about 6-7 years ago. And it works down to a second because it is very easy. You just need to make, if you have your oven heated at 400 degrees, you take the turkey out after 30 minutes exactly, let's say, or an hour later, I don't know, and you measure the temperature, you run the same calculation, it will be down. The students confirmed it. They did the chicken in Calculus 1, and this works. This is the formula that the industry uses. Guys, it's nothing, right?
Don't they usually take into account weight of the turkey too? Like, where do you take the measurement at a half hour, like within the bird?
Well, you have that probe that sticks inside and measures all the way down, and that's where that measurement, the temperature, the 79 temperature after half hour, will depend on how big bird is, because if you have a bigger bird, right, in the turkey in the oven, right, the bones, right, will be more meat, so the bones will be deeper, and it would not be 79. Maybe it would be 74 degrees or 75 degrees, right? So the smaller the bird is, the bones are closer to the surface of the meat, right, which is where the 400 degrees is. So obviously the larger bird will take longer time. Now I took all these approximate times and so on. So, but if you actually do this, you will see that everything works perfectly. Perfectly. You can't escape it. So this is just more of a kind of outline of how you could calculate and you know what? If you want to, just tomorrow, buy a $4, $5 chicken and try it. And you'll see if you actually have time and you want to show it in a household who's the boss, it's the way. So go get a $5 chicken, and if you mess it up, well, oh well, $5, right? But you will see if you carefully do it, it will be perfect. And you set the timer down to a minute and a second, right, of what your calculation said, and just walk away. When it goes ding, take it out, you measure it again, it will be exactly 165. It has to be, because that's how physics works, and it does not make exceptions. It's not English, where you don't have deers and popcorns. It's math, physics, no exceptions. Sorry. Okay, so that's that problem on turkey. And should we do something radioactive for a good measure? Half-life. We did the carbon dating, which is technically half-life, but where would we without some uranium or plutonium, right? So let's see. Uranium-238 sounds like a good okay, so uranium-238 has a half-life of 4,560 years. And they want in the textbook to know what's the K value for it. How do we compute that? Yes. Yes. Nice. Then what?
And then you would write in your numbers and put M/2 equals E and then K and then put time for 4,560 days.
Yes.
And then the M's crossed out.
And then we use ln and we're done. So ln of 0.5 negative 0.1230 1520. So 152. That's the K. Good. So those are the word problems from 3.5. They are very, very important. As you can see, they're everywhere. We talked about Advil, I believe, last time. We talked about car loans last time. We talked about carbon dating and a turkey. And here's uranium. You can talk about charging and discharging capacitors and batteries for cell phones. And else you can also talk about population. Do you see how this is everywhere? Right? We touched upon cooking and history. All right? You gotta appreciate the power of this section. All right? Not to mention finance, personal finance, and everything else that goes with it. So that concludes 3.5, and now we're going to jump into 7.1. I will restart the stream. Bye, stream.